The periodic table follows patterns, but not every element follows the rules. Let's discover why. We already know that a periodic table consists of 18 groups and 7 periods. These groups and periods contains metals, nonmetals, noble gases, metalloids, transition metals, lanthanides, and actinides. Each period and group follows predictable atomic trends. Let's start with atomic radius. Atomic radius measures an atom's size, but the electron cloud has no definite boundary. Therefore, depending on how atoms are bonded, it can be measured as the covalent radius, metallic radius, or van der Waals radius. Now let's take up electronegativity. Electronegativity is an atom's ability to attract shared electrons. Fluorine attracts them the most. Now let's see ionization energy. Ionization energy measures how difficult it is to remove the outermost electron. Now let's look into electron gain enthalpy. Electron gain enthalpy is the energy change when an atom in gaseous state gains an electron. These are the general periodic trends. But do all elements follow them? Let's find out. Some elements break these trends. Why? Let's explore the exceptions. The first exception is lanthanide contraction. Due to lanthanide contraction, hafnium has nearly the same radius as zirconium and a slightly higher ionization enthalpy. Let's see why. Pore shielding by electrons in diffuse shape for f orbitals strengthens the nucleus's pull, making hafnium smaller with a higher ionization energy. This is called lanthanide contraction. The second exception is actinide contraction. Actinide contraction makes uranium slightly smaller, with higher ionization energy and electronegativity than protactinium. Let's see why. Electrons in diffuse-shaped 5f orbitals provide pore shielding, increasing the nucleus's pull. This makes uranium smaller and raises its ionization energy and electronegativity, a phenomenon known as actinide contraction. The third exception is the d-electron pore shielding. Although gallium lies below aluminium, it has a smaller radius and higher electronegativity. Why? Pore shielding by electrons in diffuse-shaped 3d orbitals allows the nucleus to attract the outer electrons more strongly. The fourth exception is relativistic effects. Francium has a slightly higher ionization energy and more negative electron gain enthalpy than cesium. Why? In very heavy atoms like francium, fast-moving inner electrons produce a relativistic effect. This contracts the 7s orbital, expands the 5f and 6d orbitals, and causes unexpected trends in ionization energy and electron gain enthalpy. The fifth exception is stable electronic configuration. Nitrogen has a higher ionization energy than oxygen and a positive electron gain enthalpy. Why? Nitrogen has a stable half-filled 2p superscript 3 configuration. Half-filled and fully filled subshells are especially stable. The sixth exception is electron-electron repulsion. Fluorine has a less negative electron gain enthalpy than chlorine. Why? Fluorine's crowded outer shell strongly repels the incoming electron, so its electron gain enthalpy is less negative than chlorine's.